Hello everyone. Today we are going to see about the charge to mass ratio of the electron. In a previous lecture that we studied about the properties of the cathode ray. In 1897, J.J. Thomson measured the charge to mass ratio of the electron by using the cathode ray tube and applying the magnetic and electrical field on it. Just give your attention how he measured the charge to mass ratio of the electrons. Just give your attention, everyone. This one is a cylindrical glass tube. At the end of this tube, we kept the two electrodes which are connected to the external battery. This one is a negative terminal and this one is a positive terminal. As we discussed in a previous lecture, the negative terminal of battery connected to the metal plate is known as cathode and positive terminal of battery connected to the metal plate is known as anode. In a cathode ray tube, we made the cathode is perforated. Here I am making a tiny hole in a anode so that when I apply a high voltage current between cathode and anode, the gas present between them is ionized and emit the electron. That means the cathode rays from cathode to anode. Because the electrons have a negative charge, they are attracted to the positive terminal, that is anode. In anode, through the tiny hole, the rays are passing through this CRT tube. Once again, this one is a cylindrical glass tube, or you can say that extended form of cathode ray tube. At the end of this tube, we kept two electrodes or two metal plates which are connected negative and positive terminal of the battery respectively. The gas is filled between these two electrodes. When high voltage are applied to the anode and cathode, the gas between the anode and cathode get ionized and release the electron. These electrons are attracted towards the positive terminal, that is anode here. Anode have a tiny hole, so this rays just come out from this one. Here we also make a slit through which these rays are come out. This area of the tube is the inner side of this tube is coated with the fluorescent material like zinc sulfide. As we discussed, in a cathode ray tube, when any rays are strike on this fluorescent screen, it develops a bright spot. I am showing the scaling over here, so we can measure the deflection. Doing this experiment, this rays is strike on this point. I give the name of this point, supposed to be B, and develop a bright spot. In absence of electrical and magnetic field, these rays are just propagates in a straight path. Now, when I apply external electric field, positive and negative, then these rays are deflected from its original path and strike on this point, say A. This is because these rays is nothing but the rays of electron which are attracted towards the positive plate. So this shows the deflection like this. When I remove this electric field and applying the magnetic field which is perpendicular to this electrical field, and try to show this thing, it's supposed to be like this. Suppose this one is an electrical field, this one, then I applied the magnetic field perpendicular to this like this. Clear? The first position, that is electrical field, like this, top and bottom, and applying the magnetic field, that is front and back, that is perpendicular to the each other. Okay, what I observed, these rays are deflected and strike on the fluorescent screen at point C. Due to the rays of electron is attracted towards the north pole of the magnetic field. Once again, just give attention everyone. When high voltage applied to this electrode, the gas present between these two electrodes get ionized, and this ionized gas release the electron, that is a cathode rays. This cathode rays attracted towards the anode because it's positive. Anode have a tiny hole, so passing through this tiny hole, it strike on the slit, and through this slit they come out. In absence of electrical and magnetic field, these rays are strike at point B. When I applied strong electrical field, then these rays are deflected from original path and striking on the point A. The reason is this terminal is positive and these rays are the rays of electron. Remove the electric field, now apply the magnetic field which is perpendicular to the electrical field. Then these rays are strike at point C. That means they bend towards the north pole like this. Clear? J.J. Thomson may change this magnitude of electrical field and magnetic field. Increase, decrease like this. First he increased the electrical field and find the deflection. Then after he increased the electrical field, find the deflection of the cathode ray. Once again, so simultaneously he changed the electrical field and magnetic field, decrease, increase like this. Then what he found, when he balanced the electrical field and magnetic field, then this rays, it does not show the deflection and it strike at the center of this fluorescent screen, that is at the B. When electric field and magnetic fields are balanced. Once again I am telling you, Thomson changes the electrical field and magnetic field simultaneously and studied the deflection according to that change. When he balanced the electrical field and magnetic field which are perpendicular to each other, what he observed, these rays does not show the deflection and strike at the point B. Clear? Okay. Last time let's revise this whole construction and its working. Then when the high voltage applied to the electrode, cathode and anode, the gas present between the cathode and anode electrode that get ionized release the electron. These electrons attracted to the anode because the positive terminal, and this electron is passing through the slit and they come out from the cathode ray tube, and once again they passing from this slit and strike on the fluorescent screen at the point B in absence of electrical and magnetic field. When we remove the electrical field, when we apply the external magnetic field, then these rays shows the deflection and strike on the fluorescent screen at point C. Then after, by changing the electrical field and magnetic field simultaneously, J.J. Thomson measured the deflection of the cathode rays according to the changes. When he balanced the electrical field and magnetic field which are perpendicular to each other, he observed that these rays does not show the deflection and strike at the point B. Clear? let's write the theory of this particular topic. When high voltage applied across the electrode, the gas present between the electrodes get ionized. Ionized cathode rays are emitted, that is rays of electron. These cathode rays are passing through the slit and striking on the fluorescent screen at point B in absence of electrical and magnetic field. When only electric field applied, then the cathode rays are strike on the fluorescent screen at point A. When only magnetic field is applied, then the cathode rays are strike on the fluorescent screen at point C. J.J. Thomson measured the deflection of cathode rays by changing electric and magnetic field, which are perpendicular to each other. By balancing electric and magnetic field, he observed that the cathode rays did not show deflection and strike at point B on fluorescent screen. Thomson concluded that the deflection of the cathode rays, it depends on the three factors. The first one, the charge on the particles. Second, the mass of the particles. And third, the strength of electrical and magnetic field. The charge of the particle, as the much more charge on the particles, it shows the more deflection. Second, the mass of particle, as lighter particles shows the more deflection than heavier particles. Third, when we increase the electrical magnetic field, then also it shows the more deflection. When we decrease the magnetic and electrical field, it shows the less deflection. Clear? Once again, the J.J. Thomson conclude the deflection of the cathode rays depends upon the three factors. The first one, the mass of the particle. Second, the charge of the particles. Third, the strength of electrical field and magnetic field. The lighter particles shows more deflection than heavier particles. Second, the charge of the particle is more, it shows the more deflection. Third, when we increase the electric field and magnetic field, the cathode ray shows more deflection. And opposite of that, when we decrease the electric field and magnetic field, it shows the less deflection. Clear? Okay, let's write down. As we discussed, the deflections of the cathode ray depends on the three factors. That is, first, magnitude of the charge. Greater the magnitude of charge on the particles, greater the interaction with electrical field and magnetic field, greater the deflection. The mass of particle, lighter the particles, greater the deflection. The strength of electrical field and magnetic field, As we discussed, the deflection of the cathode ray increase with increase of voltage across the electrodes or increase the strength of magnetic field. Instead of that, if you decrease, then the deflection will decrease. Clear? So by calculating all these things, the strength of electrical field and magnetic field, and with other data, the J.J. Thomson derived the value of E by m, that is charge to mass ratio for the electron, and that value is 1.7588 into 10 raised to 11 coulomb per kilogram. This value is remain constant for all the type of the gas. That means the cathode ray is never dependent on the nature of the gas and the material of the electrodes. Clear? In the last property of the cathode rays, if you remember. Once again, when we measure the E by m ratio for the different gases like hydrogen, oxygen, nitrogen, what we got? We got the same answer of E by m ratio for the electrons. That means for the cathode rays, it's never dependent on the nature of gas and the material of electrodes. Clear? Okay. By using other data and strength of the electrical and magnetic field, J.J. Thomson derived the E by m ratio of the electron, that is E by m is equal to 1.7588 into 10 raised to 11 coulomb per kilogram, and if you write in a gram, then it's 1.7588 into 10 raised to 8 coulomb per gram. Charge and mass of electron. Mulliken's oil drop experiment, he found the charge of electron is 1.6 into 10 raised to minus 19 coulomb. According to J.J. Thomson, E by m 1.7588 into 10 raised to 8 coulomb per gram of the electrons implies that E by m equal to 1.7588 into 10 raised to 8. E, the charge of electron, is 1.6 into 10 raised to minus 19 coulomb. So 1.6 into 10 raised to minus 19 upon m, that is equal to 1.7588 into 10 raised to 8. Take the mass on the other side and this data in a denominator, implies that m is equal to 1.6 into 10 raised to minus 19 divided by 1.7588 into 10 raised to 8, and that is equal to 1.091 into 10 raised to minus 28 gram. This is the mass of electron. Me is equal to 9.109 into 10 raised to minus 28 gram. In SI unit, mass of electron is 9.109 into 10 raised to minus 31 kilogram. This way we can calculate the mass of electron. This whole topic, that is a charge to mass ratio, the discovery of the E by m ratio and the calculation of mass of electron, that I show you in an animation. Just go through it.
Objective: to understand how the charge to mass ratio of an electron was measured by J.J. Thomson. As you know, the atom is the smallest particle of matter, and electrons are subatomic particles present within an atom. How was the mass of an electron measured? Was an instrument used to measure it? Surprisingly, no. How then could scientists measure the mass of an electron? Let's find out. Charge to mass ratio of an electron. Once the electron was discovered, J.J. Thomson continued his efforts to calculate the charge-to-mass ratio of an electron through experiments. The experimental setup included a cathode ray tube. With a cathode, an anode and a metal plate. The anode he used in the experiment had a slit. At the end of the tube was a large sphere, coated with a phosphorescent material so that any beam after striking it would leave behind a mark on it. It was also provided with a scale to measure the deflection. At high voltage and low pressure, cathode rays were produced in the cathode ray tube. In the absence of electric and magnetic fields, the cathode rays produced were found to travel in a straight line without any deflection and struck the tube at point A. When an electric field was applied, the cathode rays were found to deviate from their straight-line path and hit the tube at point B. Similarly, when a magnetic field was applied, cathode rays were found to deviate from their normal path and strike the tube at point C. When both electric and magnetic fields were applied perpendicular to each other and to the path of the cathode rays, the rays showed deviation. Thomson observed that the amount of deviation of cathode rays depended on three main factors. 1. The magnitude of negative charge on the particle. The greater the negative charge, the greater was the deflection. 2. The mass of the particle. The lighter the particle, the greater was the deflection. 3. The strength of the electrical and magnetic field. The stronger the field, the higher was the deflection. Thomson calculated the charge-to-mass ratio of an electron by accurately measuring the deflection of electrons when varying strengths of electric and magnetic fields were applied. His efforts culminated in measuring the charge-to-mass ratio of an electron, which was found to be 1.758820 into 10 to the power of 11 coulomb per kg.